Okay, class, here's a solution to review problem number 1. This is a fourth degree polynomial written in standard form. We want to find all real and complex zeros. The first step for us, is to graph the function. That'll give us an idea where the real zeros are. So here I went ahead and typed in the polynomial in my y equals bar in the calculator. And here's what the graph looks like. Okay, so it looks like it is intersecting the x-axis at -5, and there's a turning point there. But let's just zoom out. At least let's stretch it vertically and see what's going on here, really. So I'm going to actually just increase the y max to 500, adjust the scale, and okay, we now have a better picture here. We still see that the only real zero is going to be at -5, and there's a turning point there, meaning that that multiplicity is 2. And then the other two zeros in this function are going to be complex. So let's go ahead back to our notepad and write that down. So we know there is a real zero at x equals -5, and we know that there's a turning point there, which means that its multiplicity is 2. Okay, so we need to find out that is going to correspond to this factor in p of x, and it's going to be multiplied by some quadratic. We need to use synthetic division to figure out what that quadratic is. So let's go ahead and set that up over here to the right. We're going to divide by our x, and we're going to need to do this twice, right? Because our multiplicity is 2. So let's fill in the coefficients of the polynomial. We have 1 x to the 4th plus 4x cubed minus 22x squared minus 20x plus 325. Go ahead and do our synthetic division. The 1 goes down to the bottom. -5 times 1 is -5, giving us -1 when we add that to 4. -5 times -1 is a +5, gives us a -17 when we subtract 22 from that. -5 times -17 is 85. When we subtract 20, we get 65 left, and -5 times 65 is a -325. That gives us a 0 remainder, and so now we've got a third degree polynomial left over, but we need to divide by -5 again using synthetic division, and that is because the factor x plus 5 we know is in the polynomial twice as a factor. So let's go ahead and keep going, do another round of synthetic division. We've got -5 minus 1, that's -6. -6 times -5 gives us a +30. Subtracting 17 from that gives us -13. Sorry, that is a +13. +13 times -5, that gives us a -65. Again, we've got 0 as the remainder, and now we have a quadratic. This we can go ahead and plug in here for p of x. We've got x plus 5 squared, and our quadratic is x squared. I'm just taking the coefficients here of what we came up with after synthetic division, minus 6x plus 13. Okay, so to find out now what our complex zeros are, we need to look at this quadratic and find out the values for x that make that 0. And to do that, we need to use the quadratic formula. Okay, so using the quadratic formula, which is x equals -b plus or minus square root of b squared minus 4ac all over 2a, we get the following. X equals negative times a -6 plus or minus -6 squared minus 4 times 1 times 13 over 2 times 1. This can be simplified. A negative of a negative 6, that's a positive 6, plus or minus the square root of negative 6 squared is 36, minus 4 times 1 times 13, that is 26 negative, that's minus 52. Take the square root of that. 2 times 1 is 2. All right, we're getting closer. We can distribute the 2, so 6 over 2, right? 6 over 2 plus or minus 1 over 2 times the square root of 36 minus 52. That equals negative 16 equals, all right, 6 over 2 can be simplified to 3, plus or minus 1/2 times the square root of negative 1 times the square root of 16 equals 3 plus or minus, well, the square root of negative 1, that's just I, and the square root of 16 is 4. So we've really got plus or minus 4 over 2i, and of course 4 over 2 can be simplified to 2. So we have 3 plus or minus 2i as our two complex zeros, in addition to our one real zero of this. So here are our complex zeros.